For your introduction. This is a joint work with my student, Dongye Wu. Okay, first let me give you some introduction to QCCD architecture. Trapped ion system offer a uniform qubit quality, long coherence times, and O-to-O connectivity within and trap. The QCCD architecture consists of multiple traps connected together. And in this work, we focus on QCCD devices in linear topology. And this slide shows a very tiny example for QCCD device. Here we have 3 traps. They are connected in a linear fashion. And within each trap, there are ions confined inside it. And for this example, the maximal capacity for a trap is 3. So for the trap T0, it is at full capacity, while for the trap T1 and T2, they have some available capacity, which are 2 and 1. And in QCCD system, a 2-qubit gate can only be executed when both qubits are in the same trap. If not, shuttle operations are required to move ions to the same trap. To shuttle an ion to an adjacent trap, 2 conditions must be met. The first one is the ion must be located at the edge of the current trap on the side facing the destination trap. Otherwise, a swap gate is required. The second condition is the destination trap must have available capacity to accommodate the ion. Here, let me show an example to illustrate shuttle operation. In this example, we would like to move ion 1 from T0 to T1. And first, we have to swap ion 1 and 3 to make ion 1 get to the right edge of trap T0, and then we have then we perform a shuttle operation to move ion 1 into T1. Since ion shuttling at delays raises motional energy and degrades gate fidelity, minimizing shuttle count is a primary optimization goal. Here, let me quickly define the problem addressed in this paper. The input consists of a quantum program, the hardware configuration, and an initial qubit placement. And the output is a valid sequence of operations for executing the given quantum program. And the objective is to minimize the amount of required shuttle operations. And in the bottom, here is a tiny example for for this problem. Here we have a quantum program consists of 4 gates, and also we have 2 traps connected, and each trap has the capacity of 3 here. And on the right is a possible output of the problem. As you can see, it needs 1 swap gate and 1 shuttle operation. Okay, now let me quickly explain the overall flow of our approach. At the beginning, we will construct a gate dependency graph based on the given quantum program. And then we will assign every gate an index based on a topological order from the gate dependency graph. And now we are going to schedule every gate in the iterative manner. That means we try to schedule gates 1 at a time. And at each iteration, we will find a target gate to schedule based on a from layer method. And if the target gate doesn't need shuttling, then we can append the gate to the output sequence. Otherwise, if the target gate needs shuttling, then we will check whether there exists any traffic block that could prevent ion from shuttling. If traffic block does exist, then we will resolve it. And after that, we will find a destination trap for ion to move to. And the destination trap selection method basically will based on a look-ahead guess set. And once we have determined the destination trap, we will check whether that trap is full. If it's full, then we have to resolve it. And here we use several existing techniques trying to free up space in the destination trap. And once the destination trap has enough space to accommodate the ion, then we can add the shuttle operation and then append the gate into the output sequence. And once the target gate is scheduled, then the gate dependency graph will get updated by removing that particular target gate as well as its outgoing edges. So the whole process will be iterated until the dependency graph becomes empty, meaning that all gates have been scheduled. Okay, now let me quickly give you some details of our approach. This figure shows an example of the gate dependency graph. Basically, every node in the graph represents two qubit gates. And if they're aged between two nodes, meaning that they have the execution dependency between these two gates. And at each iteration, a remaining gate is in one of the following three states: block executable and or shuttling required. A gate is in block state, meaning that the gate has no incoming edges in the gate dependency graph. And the gate is executable means that the gate has no incoming edges in the gate dependency graph, and also its qubits are in the same trap. If a gate is in shuttling required state, it means the gate has no incoming edges in the gate dependency graph, but its corresponding qubits are in different traps. So we can, based on the state of each remaining gate, we can find the so-called from layer, which consists of gates. They are either executable or shuttling required. And on the right is an example to illustrate the gate state and the from layer. And for the from layer, there are two possible cases to consider. The first one is one or more executable gates are in the from layer. In this case, then one of the gates can be selected as the target gate. And since it doesn't need any shuttling, then we can append this gate to the output sequence. The second case is that all the gates in the from layer are shuttling required. So for this case, we are going to select the gate with the smallest index from the topological order as the target gate. So if the target gate is shuttling required, then we have to check whether there exists any traffic block. And if any traffic block exists, then it has to be resolved. And here we have two possible cases for traffic block. In this example, we assume ion 0 and ion 4 are qubits involved in the target gate. And for the first case, because the T1 is in between T0 and T2, and it doesn't have any available capacity, so T1 will become a traffic block. So we are going to move one of the ion from T1 to T2. And the second case is that both T0 and T2 are at full capacity. In this case, then again, we are going to fill up the space for T0 and T2. So as the figure shows, for T0, we will move T2 to T1, and for T2, we are going to move ion 6 to T3, so to make every trap to have available capacity. And to determine a beta destination trap, in the gate dependency graph, all gates reachable from the target gate within a user-defined depth are identified. And then among those gates that have any common qubit with the target gate are selected and included in the so-called look-ahead get set. And this example shows that those gates in the green color are included in the look-ahead get set for G1 when the user-defined parameter n layer is set to 3. And now let's assume the target gate has qubit A in trap TA and qubit B in trap TB. For each trap I, we define GAI as the number of gates in the look-ahead gate set that involve ion A and another ion in trap I. And similarly, we can define GBI. And for each trap I, we will calculate a score as follows. And this score actually will estimate the amount of look-ahead gates that can be executed in trap I after moving ion A and B to trap I. And the trap with the higher score will be selected as the target trap. If the target trap is located between trap TA and TB and its available capacity has at least 2, then this trap will be selected as the destination trap. Otherwise, one of TA and TB will be selected as the destination trap. And here, again, we modify the score function a little bit, and the trap with a higher score will be chosen as the destination trap. If the destination trap has no available capacity, then we will apply existing method to resolve it. Okay, now let me move on to the experimental results. Our approach was implemented in Python, and it was evaluated on 12 actual circuits and 121 synthetic circuits. And those synthetic circuits actually include a QV and 120 random circuits. And there are 4 possible sizes for random circuits, 60, 65, 70, and 75, indicating the number of qubits. And those test cases were from either the literature or open source repositories. And for the hardware model, we adopted a linear QCCD architecture that consists of 6 traps. Each trap can initially accommodate up to 15 ions and have 2 additional slots reserved for shuttling. And this table shows the results of shuttle count and compilation time of our approach. We also compare our approach with a previous work that was published in date 2022. And as you can see, for the shuttle count, our approach outperformed the previous work almost for all test cases. And the maximum shuttle count reduction rate can reach close to 38%. Regarding the compilation time, again, our approach is faster than the previous work. And I think the maximal speed up, the maximal runtime reduction can be close to 75%. And on average, the shuttle count can be reduced by 16.44%, and compilation time can be reduced by 30.77%. Okay, now let me make a very short conclusion. In this paper, we present an ion shuttling approach for linear QCCD topology featuring a novel target gate selection and destination trap selection. And the experimental result demonstrate the efficacy of our approach in terms of shuttle count and compilation time. This concludes my talk. Thank you for your listening.
Thank you very much. Questions, please?
So at the beginning of the work, you had already assigned your qubits 0, 1, 2, 3, 4, 5. Maybe by changing the order of those, you can reduce the number of swaps?
Those initial mapping is given as the input.
Okay.
Yes. No, right. But if you want to do the shuttling, you have to swap. If the ion is not at the edge, then you have to do some swap. Okay.
Thank you.
Yeah. So, so being from IBM, I only really know superconducting qubit systems, correct? So maybe this is not the right question for an ion-based system. But I think you can only swap to neighboring traps, correct? And I think in your examples, you show mostly linear systems, correct? The QCCD. So is that a fundamental limitation of an ion-based system, that they have to be linear, or can you have more complex topologies as well, so you can swap to other traps?
Oh, I think there are different kinds of topologies. But here we only focus on the linear one. Okay.
Okay.
Yeah.
My question was similar. Is there any topology where you can clone gates?
Any topology?
Make copies of the gates, so you can do more parallel.
Gates don't really exist physically.
No.
I'll also make one question. Why do you change the trap score to trap score prime, and you don't use the previous trap score that you had computed?
Oh. I think the previous work, okay, they also have a score to calculate which trap should be selected as the destination. But they restrict the destination trap to be chosen from the two traps that have ions involved in the target gate. For example, if you have a target gate whose qubit are located in trap TA and TB, then the previous will only try to move either one ion from TA to TB or from TB to TA. But in our work, we allow the ion to be shuttled or to be moved to any trap between these two.
Yeah, my question was more about why you change the trap score between 2 points in the algorithm and you don't keep the same one.
The trap score?
The trap score to trap score prime, but we'll continue offline.
Okay.
Thank you for your... Let's thank the professor.